All right, so hello, we are recording. We are live with block 4, minus the sophomores. Okay, all right. So at this point, we are going to finish up section 4.1. So if everyone can take out their notes, please. So we are looking at I think we've got about 3 more topics in section 4.1, and then maybe we'll move on to section 4.2, which I dearly hope we will. So in section 4.1, and you notice I'm not wearing this headset because it just bothers me to wear it. So I'm just holding it. Thank you. All right. So consider a particle that is moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed of the particle is given by this formula. I would at least get that formula written down. All right? Linear speed is going to be arc length divided by time. So for example, if we have a circle, and let's say there's a little... Hello. Let's see, something for Emily, something for Chad. Emily C. Okay, so if we have a circle and we are like a little ant right here on the circle, and we are going to be traveling this far around the circle, for example, where that distance is s for arc length. Focus, please. And if it takes us, let's say, 20 seconds as a little ant, it takes us 20 seconds to traverse that distance, and let's say that happened to be maybe 2 radians, for example, then our linear speed would be 2 radians over 20, whatever I said, 20 seconds, right? That would be the linear speed. How fast we are moving around a circle, all right, is linear speed. All right, so if theta is the angle in radian measure corresponding to the arc length, corresponding to the arc length s, then the angular speed of the particle is given by a different formula, and that is angular speed equals central angle divided by time. All right, so again, so linear speed and angular speed. And so this time, if we're looking at angular speed, we are talking about how fast an angle is changing, the motion. So we want the angular speed might be, well, that it's probably best described with an application that we're going to take a look at. All right, so bottom line. Linear speed measures how fast the particle moves, and angular speed measures how fast the angle changes. That is the difference between linear speed and angular speed. Let's take a look at an example. All right. The second hand of a clock is 8 centimeters long. Find the linear speed of the tip of this second hand as it passes around the clock face. All right, the second hand of a clock is 8 centimeters long. Find the linear speed of the tip of this second hand as it passes around the clock face. So let's say here is the second hand on a clock. All right, and this second hand is going to be, say it's exactly this long, and that has a length of 8 centimeters. We want to find the linear speed of the tip of this hand as it passes around the clock face. So how fast is the tip of the hand moving around the clock? Well, we would need to use our formula for linear speed, which is what? Linear speed is S over T. What is the arc length in this case?
2 pi.
Well, okay, arc length, remember we need to use this formula. Arc length equals radius times theta. What's our radius? 8. And if we're going one time around the circle, that's an angle of what? 2 pi. Remember we are using radians. All right, so that gives us 16 pi. Everybody with me? Divided by, we said going all the way around the circle. How long does it take for a second hand to go around the circle? 60 seconds, right? So you could either say 60 seconds or 1 minute, however you want to express your units. By the way, this was 16 pi. What units was that? Arc length measured in linear units. We're talking about the distance around the clock. Centimeters. So that means our final answer, can I get a decimal approximation for this, please? 16 times pi, use the pi button, divided by 60. If it's a real world problem, I'm okay with decimal answers for this. What'd you get? 0.84. 0.84. Do people agree? 0.84. Do we agree? And what units are we talking about?
Centimeters per second.
Centimeters per second. Are we all right with this? Okay. All right. And first find the arc length. We did that. I didn't show you what we talked about. Okay, so let's talk about this example. The circular blade on a saw rotates at 2,400 revolutions per minute. Find the angular speed in radians per second. All right, so we're trying to find the angular speed. What's our formula for angular speed? All right, angular speed is central angle divided by time. So we have this circular blade for the saw, and the angle, we go around this circle, the circle spins 2,400 times per minute. You with me? It's spinning that fast. It's making a complete revolution 2,400 times per minute. So we need to get a measure for the angle that's been traversed in 1 minute. You with me? So if it's 2,400 revolutions, how many, what would be the radians in 1 revolution? 2 pi, so I could write this as times 2 pi radians per 1 revolution, right? The revolution units are dividing out, and I'm getting my total angle, right? My central angle is what? Yeah, 4,800 pi radians. Does that make sense? So that's my central angle. Oh, I didn't write angle. Central angle. So I'm going to have my answer as 4,800 pi radians divided by what? Oh, we want it in terms of seconds. 60 seconds. All right. And so we get, I don't know, 60 goes into 61, so into 4,800 is at 80. So I get 80 pi radians per second. And what would that be as a decimal? 251 radians per second. Are we okay with this? A very fast angle change, right? The angle is, we're traversing 251 radians every second. And you know how big a radian is, right? By the way, did we ever get a decimal approximation for a radian? How would we get a decimal approximation for a radian? How many radians are in one circle? 1 radian equals what? Is what we're trying to find out. Well, 1 complete revolution of a circle is what? So 2 pi radians is equal to how many degrees? 360 degrees, right? So how am I going to get 1 radian? What am I? Divide by what? Divide by 2 pi? So what is 360 divided by 2 pi? Calculators, we want to get a decimal approximation. So 1 radian is approximately how many degrees? We're taking 360. 57.3. What units? Degrees. So remember last time when we were showing what a radian is, just a quick reminder, if this is our radius r and we have an arc that is exactly that same length of r, you with me? Focus please. Then this angle that I just cut off would be 1 radian. Everybody agree from what we talked about last time? And that angle that I just drew, which is 1 radian, also measures how much in degrees? How many degrees is that? 57.3 approximately. Everybody agree? Does that make sense? So when you're talking about 1 radian, think of about 57 degrees approximately. Okay? All right, so are we okay with this example? So far so good, but we've got a follow-up question. What if the blade that's spinning around on this circular saw, what if the blade on this circular saw has a radius of 4 inches? Find the linear speed of a blade tip in inches per second. So you're picturing this circular saw, and it's spinning, and it's got these ultra sharp blades, right, like this, and it's spinning really fast. And the blade tip is, or I should say, the blade itself is 4 inches long. You with me? Yeah. Okay, so we want to find the linear speed. You know, some little ant is going for the ride of his life here. He is at the tip of this blade, and he is spinning around 2,400 times every second, and we want to know what's his speed. Does that make sense? So how are we going to find that? What's our formula for linear speed? Linear speed is S, which is arc length, over T, which is time. So we need the arc length that's traversed by this blade as it spins around. So how do we find that? What's our formula for arc length? Radius times theta. What's our radius? 4 inches. And what's our angle measure? Didn't we calculate that already? What was it? 4,800 pi, right? Was our total amount of angle that we traversed. So 4,800 pi. And then we're dividing, well, that's our arc length, which is, what's 4 times 48? Thank you, 19,200. What units are we talking about? Inches, right? That's how far, that's the distance that little ant's traveling in 1 minute. Or is it 1 second? 1 minute? 2,400 times. In a minute? Okay, so that's how many inches he's traveling in 1 minute. Does that make sense? Yeah.
You multiply by pi.
Did I miss something? Oh, I need this times pi?
Yeah.
So it should be 19,200 pi inches. Is that right?
Yeah.
In 1 minute?
That's why I said pi.
Gotcha. Okay, so we get, oh, but we want, hang on a second, we wanted inches per second, so I better change this to what? 60 seconds. Can I get a decimal approximation for the speed of this little ant who is riding on the tip of the blade as it spins around 2,400 revolutions per minute? Pull.
No,
Pull.
sir.
1,005.31. What units are we talking about? Inches per second. Are we okay with this? All right, awesome. Okay. All right, that brings up our last topic from section 4.1, which is the area of a sector of a circle. Do you know what a sector is?
It's like a certain area of a circle. No.
Well, it's like a wedge. Picture it like a wedge of a circle. So for example, a sector of a circle might be a piece that looks like all of this here, right? That would be a sector of the circle, right? So we're looking for a fractional part of a circle. All right, we have a formula for to find the area of a sector of a circle. For a circle of radius r, the area A of a sector of the circle with central angle theta is given by, I give you two formulas, all right? One is 1/2 r squared times theta, where A is the area of the sector, r is the radius of the circle, and theta is the central angle. And this angle here, if you use this formula, this is for if theta is in radians. So if you're given certain radians, like let's say, oh, this is, let's say 4 radians. Well, then we would want to use this formula here. All right, and let's say this radius here was 6. Well, we get 1/2 times 6 squared times 4 radians. But if you were given the central angle in degrees, then you can use this formula here. You take the degree measure divided by 360 and multiply by pi r squared.
So thetas and radians used for one.
Right.
Degrees used.
Right. So if you're given the central angle in radians, you're going to want to use this formula. And if you're given the central angle in degrees, this would probably be the easier one. Otherwise, you're going to have to convert to radians and then use the first one. Okay, are we all right with this? All right, let's take a look at this example. A sprinkler on a golf course is set to spray water over a distance of 75 feet, and it rotates through an angle of 135 degrees. Can you find the area of the fairway watered by the sprinkler? So if you are picturing the situation here, we have about 75 degrees is about maybe like this. All right, and here's the sprinkler, and it's going to spray all of this area. You with me? Oh, I was doing 75 degrees. My bad. So if it's 135 degrees, it might be more like this. All right, and this is 75 feet. Is that right? All right, so we're spraying all of this area with water here, and we want to know the area of that fairway that's getting watered by the sprinkler. So you could do this in 2 different ways. As a matter of fact, I tell you what, let's have the ladies in the room convert the 135 degrees to radians first, and then use the left formula. Come on, ladies, you can do this. And gentlemen, you can use you can use the other formula, the one on the right. All right? All right, gentlemen, did you get an area? Cole?
6,626.8 feet squared.
6,626.8
Feet squared.
feet squared.
Oh, yeah.
Square feet. Do people agree?
Oh, yeah.
All right, ladies, do you agree with that answer? And ladies, you did this by converting 135. Did you multiply by pi over 180? And you got what? What is it? 3 pi over 4. And then you took 3 pi over 4, plugged it in right here, and multiplied by the radius squared. God bless you. Radius squared, 75 squared, times 1/2. Is that also turn out to be this answer? Ladies, yes? Are we okay with this? Awesome. Okay, so okay, that wraps up section 4.1. I would like to take a look at a little bit of section 4.2. So let's do that. All right, section 4.2 is your introduction to the unit circle, trig functions based on the unit circle. All right, your learning objectives, which you do not need to write down. You are to learn to identify a unit circle and describe its relationship to real numbers, evaluate trig functions using the unit circle, use the domain and the period to evaluate sine and cosine functions, and use a calculator to evaluate trig functions. All right, so those are learning objectives. You do not need to write those down. All right, so first of all, what do we mean by a unit circle? A unit circle is a circle with radius 1, which is why we call it a unit circle. It's got a radius of 1, and it's centered at 0, 0. The equation of such a circle would be, as you know from our study of circles earlier this year, would be x squared plus y squared equals 1. Everybody agree? Remember the formula? X minus h plus y minus k quantity squared equals the radius squared. Everybody agree? So if our radius is 1 and our center is 0, 0, that gets us to this equation right here. Okay? So that's this circle right here. Here's the x-axis right here. Here's the y-axis. Whoops. Here's the y-axis right here. So this point right here is 0, 0. Everybody agree? All right. So that's our unit circle. So with that in mind, can we find out, and kind of just ignore this line for just a moment, what would be these ordered pairs that I'm putting up here? What's this ordered pair going to be right here? 1, 0. What would this ordered pair be right here? 0, 1. What about this one? Negative 1, 0. What about this one? 0, negative 1. Okay? Now, imagine that a real number line is wrapped around this circle with positive numbers corresponding to counterclockwise rotation and negative numbers corresponding to clockwise rotation. All right, so picture this is the real number line. I can't separate it, but this one right here is the real number line that we're talking about. This is a real number line right here. So for example, you know, maybe 1 might be right here, 2 might be right here, 3, you with me? And over here, like negative 1, negative 2, negative 3, and so on. Okay? So picture this real number line, and if we wrap the real number line around the circle, okay, the real numbers on the number line are going to touch the circle at a certain point on the circle. Does that make sense? So for example, this 1 right here is going to fold over as I'm folding this line around, and it's going to touch the circle maybe right about here. You with me? And the 2, for example, is going to, you know, if I fold this whole line over, the 2 is going to touch down right about here, and so on. Okay? As the real number line is wrapped around the unit circle, each real number t on the number line, like 1, 2, 3, all those numbers, will correspond to a point x comma y on the unit circle. Okay, so there will be some number that will touch right down at 0, 1. And a little further up, there will be another number that will touch down right here at negative 1, 0 as we wrap it around. Does that make sense? All right, so if we have t equals 0 on the number line, keep my number line there in my unit circle, t equals 0, this is the number on the number line. Number on the number line, I'm abbreviating, would correspond to what ordered pair on the circle? Cole? 1, 0. So 0 on my number line, I didn't draw that one in, but that would be right here, right? This is 0 on my number line. It touches down right here at this ordered pair 1, 0. Agreed? So that goes to 1, comma 0. All right. What about 2 pi? Where's 2 pi going to wrap around to? 1, 0 again, right? It's going to wrap all the way around to 1, 0 again. God bless you. In general, each number t also corresponds to a central angle whose radian measure is also t. All right. In general, each real number t on the number line is going to correspond to a central angle theta whose radian measure is also t. So we can talk about t, let's talk about 2 pi units up the number line and wrapping it around, and it's still going to be touching down at 1, 0, and that angle is also 2 pi units, 2 pi radians. All right, so we have our formula, theta equals s over r, that you're already familiar with, which we can write as s equals r theta. And if our radius is equal to 1 here, because it's a unit circle, right? And this is our arc S, would you agree that theta is just going to be equal to S? If I use this formula and I plug in a radius of 1 for r, don't I just get that the theta angle is equal to S, the arc length? Does that make sense? So we're tying in that real number line right here that's attached to the unit circle with 0 on the number line corresponding to 1, 0, and the fact that any number on the real number line is going to be exactly the same as the angle measure, because the arc length is going to be the distance up the number line, and the angle measure is the angle that's covered. All right, so t is the length of the arc, and t is also the angle measure in radians. All right, are we ready? All right, since every real number t corresponds to an ordered pair on the circle, and that ordered pair would be x comma y, we can define 6 different trig functions where t is the input and something about the ordered pair is going to be the output. Maybe it'll be the x coordinate of the ordered pair. Maybe it'll be the y coordinate. Maybe it'll be the reciprocal of the x coordinate. Or maybe it'll be the y divided by the x. There's 6 different things we can do to the ordered pair and 6 different trig functions. All right, so let's talk about these. Here are the 6 different trig functions: sine, cosine, tangent, cotangent, secant, and cosecant. These are the 6 different trig functions. And we abbreviate all of these 6 trig functions with 3 letters each. All right, so when we talk about the sine of an angle, we will write sine, S-I-N. We do not pronounce it sin, we pronounce it sine. All right, but it's still abbreviated with 3 letters. Cosine, we abbreviate with 3 letters to C-O-S. We never say cos. We read it cosine, but it's written C-O-S. Same thing with tangent. Tangent is abbreviated T-A-N. We never say tan, we say tangent, but we write it T-A-N. Cotangent is written C-O-T, but it's pronounced cotangent. All right. Secant is S-E-C, but it's pronounced secant. And cosecant is C-S-C. All right. So those are the 6 trig functions. Now we need to talk about what's the relationship between these trig functions and the real number t. So first of all, remember, the t values are going to be on this number line. All right, so these are the t values. Maybe 1 is here, maybe 2 is here, and so on. All right, these are our t values. And they're going to map to some ordered pair on our real number line. Like, let's say the ordered pair here is x, comma, y. All right, once a real number, t, touches down on the unit circle at some ordered pair, then we can talk about a trig function for that real number. So the sine of angle t, is always going to be the y coordinate. All right. The sine of angle t is going to be the y coordinate. The cosine of, I say angle t, or the real number t on the number line, the cosine is the x coordinate. All right, the tangent of the real number t is going to be the y divided by the x. The cotangent of a real number t is going to be the x divided by the y. The secant of t is, I'm missing an equals there. The secant of t is equal to the reciprocal of the x, so 1 over x. And the cosecant of t is equal to the reciprocal of y. So cosecant of t is 1 over whatever the y coordinate was. All right. The domain for sine and cosine are going to be all real numbers. The domain for these is going to be all real numbers. Plug in any number you want on this number line, and you can state what the sine of that number is or what the cosine of that number is. Well, not so with the other trig functions. All right, because some of the other trig functions, if x happened to be 0, we can't divide by 0, so tangent would be undefined wherever the x coordinate is equal to 0. Cotangent is going to be undefined wherever the y is equal to 0, and so on. So which trig functions are reciprocals of each other? Tangent and cotangents are reciprocal of each other, sure. These are reciprocals. What else are reciprocals of each other? All right, secant and cosine are reciprocals of each other. And sine and cosecant are reciprocals of each other. All right. So we said tangent and cotangent are reciprocals. Sine and cosecant are reciprocals, and cosine and secant are reciprocals. All right, so when is the tangent undefined? Whenever the what, Cole? Whenever the x equals 0. When the x coordinate of our ordered pair equals 0, right? When is the secant undefined? When is the secant going to be undefined? I need to get my popsicle sticks out. I think I will. Emily H. So same thing, right? When the x is equal to 0, all right? When is cotangent going to be undefined? What do you think about that? When is the cotangent going to be undefined? You're looking back at your notes. Alyssa. All right, when y is equal to 0. All right, and what about cosecant? When is cosecant undefined? What do you think, Cole? Same thing, when the y is equal to 0? All right. When the y coordinate equals 0. Okay, so here's the deal. Now we need to start learning what some of the trig functions are for various values around the unit circle. So on your paper, can you draw a circle, and let's cut from 0. We're going to cut from 0 to pi. Remember, here's 0, here's pi. We're going to cut from 0 to pi up into 4 equal pieces. In other words, we really want a circle cut into 8 equal pieces altogether. So in order to get the ordered pairs that are going to be at each one of these places, so that we can figure out the trig functions, we need to investigate the idea of the fact that this would be the x here, this would be the y, to get to this ordered pair, xy. Everybody agree? And if this is our unit circle, we already said what this ordered pair is right here. What's this ordered pair? 1, 0. What's this ordered pair up here? 0, 1. What's this ordered pair? Negative 1, 0. What's this ordered pair? 0, negative 1. So now we're trying to find these other ones. This one, this one, this one, and this one, right? We're trying to find those values. So to get this one right here, we need to go this far over from 0, 0. Remember, 0, 0 is right here. This far over, that's the x, and this far up, that's the y. All right? What do we notice about this? Well, if this is, we said this corresponds to what in terms of radians? Here's 0, here's pi, so this would be what? Pi over 4. So this is pi over 4. By the way, what's pi over 4 in degrees? Well, that would be 1. 1 radian is 57 point something. But pi over 4, convert it. If you do pi over 4 radians times 180 degrees over pi, what do we get? 45. So it's 45 degrees. So this angle here is really a 45-degree angle. You with me? And that means this angle here is what? 90. And so what's this angle? All right. Now, did you take geometry? Do you know something about a 45, 45, 90 triangle? X, X, and then X radical 2. You remember that? So this is this length and this length are going to be the same, and this length is going to be, if this is X, this is going to be this. I'll use R. I'll use R. and this would be r squared root of 2. Agreed? But our r squared root of 2 is the only side length that we know right now. What is the length of this side? 1. Why is it 1? Because it's a unit circle. So that means that r radical 2, this is actually equal to 1. So how are we going to find out what x is and what y is? Remember, they're got to be the same because they are the legs of an isosceles right triangle. Yes? So they have to be the same. So how are we going to find that out? I'm going to kind of blow this triangle up a little bit, or at least look at it over here. So here's my 45, 45, 90 triangle where the hypotenuse is 1. What do I need to do to find this length here and this length? Divide by radical 2. So if I knew this length, I could multiply by square root of 2 to find this length. But if I know this length, I've got to divide by square root of 2 to find this one. So when I do that, I get what? Okay, but we want an exact answer. We need to, so, all right, so it's going to have to be 1 divided by square root of 2, agreed? And this one is going to be 1 divided by square root of 2. But we're going to have to simplify that. We don't like radicals in the denominator. So what do we do to simplify 1 over square root of 2? All right, multiply by radical 2 over radical 2. So we get square root of 2 over square root of 2 over square root of 4, which is 2. So we just found out that x is equal to square root of 2 over 2, and y is equal to square root of 2 over 2. You with me? So that means we can now write in this ordered pair here. Oh boy. We can write in this ordered pair here as square root of 2 over 2, comma, square root of 2 over 2. Does that make sense? See how we got that using a special right triangle from geometry, Maria? We decided that we were taking a circle and cutting it up into 8 equal pieces, 4 on the top, 4 on the bottom. We know from our work last class that from here to here, this angle is pi radians. And since we're cutting it into 4 equal pieces, that means from here to here is pi over 4. From here to here is going to be, I didn't write it down, but what would that be? Pi over 2 is up top. From here to here would be what? 3 pi over 4, and we should number all the way around the unit circle. So what's this one? 4 pi over 4, which is pi. What about down here? What would this one be? 5 pi over 4. What would it be down to here? 6 pi over 4, which reduces to 3 pi over 2. And then to get to this point, we would get 7 pi over 4. Back up here is 8 pi over 4, which is also 2 pi. Everybody agree? Maria, does that answer your question? Is that okay? And then we said, well, if it's pi over 4, what is that in terms of degrees? It turned out to be 45. And then if that's a 45-degree angle, then we know we've got a 45, 45, 90. And we're in business for trying to find these ordered pairs. Okay, so this one is square root of 2 over 2, square root of 2 over 2. What would this one be over here? Keeping in mind we got the same a congruent triangle with it over on this side, right? It's also going to be a 45, 45, 90. Alec?
Negative square root of 2,
All right, negative square root of 2 over 2, comma, positive square root of 2 over 2. Right? For 3 pi over 4. What about at 5 pi over 4? Which my triangle, this is not looking very good. My picture was not very good, but you get the idea. So what would 5 pi over 4 be? What's that ordered pair going to be?
Gotcha.
Steph? All right, and what about at 7 pi over 4? What's that one going to be, Allison? Everybody agree? Okay, so That will give you the trig functions. Really, now we found trig functions for 8 different places on the unit circle, right? 0, pi over 4, pi over 2, 3 pi over 4, pi, and so on. So now we can start talking about the trig functions at these places, now that we found the ordered pairs. So you've got your unit circle that you just drew, so I don't need to keep this one up here right now. But I'm going to ask you to tell me, for example, what's the sine of pi over 4? What's the cosine of 3 pi over 4? What's the tangent of 0? What's the secant of 5 pi over 4? What is, well, I'll hold off right now. Let's start with these. What about the sine of pi over 4? So you get the idea. You're going to tie together our rules for the trig functions. The sine is the y coordinate. The cosine is the x coordinate. The tangent is the y over the x. Right? All those rules that you wrote down. And you've got to be looking at your unit circle to see what the ordered pair is. All right? So what is the sine of pi over 4? What's that going to be? Megan? Radical 2 over 2. The sine of pi over 4 is going to be the y coordinate at pi over 4. So it's this number right here. So we get square root of 2 over 2. Everybody with me? All right. So what about the cosine of 3 pi over 4? Nikki?
Radical 2 over 2.
Radical 2 over 2. Do people agree?
No.
It would have to be negative. Remember, cosine is the x coordinate, and 3 pi over 4 maps to right here. So we need this x coordinate here. So that's going to be negative, negative square root of 2 over 2. Does this make sense? All right, what about the tangent of 0? I hear 0, I hear undefined. Tangent is the what over what? All right, so I want the, let me slide this over here. The tangent is going to be the y coordinate over the x coordinate. The ordered pair at 0 is 1, 0. This is your x, that's your y, so I need 0 over 1, which is 0. Are we okay with this?
What?
Question.
0. Is that like the middle of the circle at 0, 0?
But the number line itself, the number line is right here. Where is it? Let me draw. I'm trying to get this to lock in. Right, that's our number line. So here is 0 on our number line, right here. Right, does that make sense? That's. So we're talking about, when we say what's the tangent of 0, we're talking about when we have 0 on our number line, not 0, 0, the center of the circle. That's going to be nothing to us because we're only interested in points on the circle, and we're interested in where the numbers on our real number line will map to the circle. All right, so we've got that one. What else? How about secant of 5 pi over 4? So I need to go to 5 pi over 4, which is here, and I want 1 over the x, is that right? So I want 1 over this negative square root of 2 over 2. And so I can multiply by the reciprocal, and I get 2 over a negative square root of 2. True? And then I want to simplify that, so I'm going to multiply by square root of 2 over square root of 2. So I'm getting what? It's going to be 2 radical 2 over negative 2. Does that look right? The 2's are dividing out, and I'm getting negative square root of 2 as my answer. So the secant of 5 pi over 4 is negative square root of 2. Not square root of 2 over 2, just negative square root of 2. Agreed? All right. And did I give another? So did you get the idea of what you're doing? Okay, so I think this is probably enough for today. Next class, we will be looking at splitting the we split this circle up into eighths, right, which are pi over 4s. Next time we'll split it up into 12ths, so we'll have pi over 6s, and we'll look at what those order pairs are going to be. All right, meanwhile, I'm going to give you your homework assignment, and oh wait, I have an exit ticket for you. Okay, so I'm going to stop, and you have an exit ticket.